In this scenario, we will have a spacecraft that's orbiting the Earth, and we want the spacecraft orientation to match the hill frame. So we're not using actual control torque to make it stabilize and then begin to track a hill frame, but rather we're just saying, look, match it precisely. The reason is we can take much bigger time steps now, and we don't have to go to like 10 Hertz integration just because of the control transients require that. When would you use this? Let's say you're doing a mission analysis and you're just trying to figure out if the spacecraft is flying in this orbit and always tracking the hill frame, and there's solar panels attached, for example. Maybe you want to do this calculation quickly, run through the scenario, and then look at it going, well, assuming perfect tracking, how much power would you actually generate? You don't want to have to run 10 Hertz. You might want to run much bigger time steps and to get that information that you're looking for. So that's just one example. So how do we do that? As before, we can actually take our attitude and a reference attitude, and we can connect it to the optional spacecraft input message, an attitude reference input message. And this will override whatever the attitude dynamics does and just say, nope, it's pointing left. We're going to do hill pointing. So we do need to bring in the actual spacecraft estimate. Where is it? So it can compute a hill frame. And from the gravity vector, that's an optional thing. You could bring in its location. And then we can have this other module that's an option. It'll run in both configurations. You could take the hill pointing output reference message directly connected to the spacecraft, and that would do it. The attitude ref correction is nice because if you're driving the attitude directly with R, you may not want to line up B with the reference frame. Maybe you don't want B1 to become equal to R1 and B2 equal to R2 and so forth. Maybe R1 should become equal to B2 and R2 should become equal to B3 because you want it to be rotated. You know, there's a static offset. With attitude tracking error, you can put in that fixed attitude correction. But if you directly generate a reference attitude, it generates a hill frame, and that has a classic 1 is radial, 2 is along track, 3 is orbit normal definition. So if you want something else, we made this attitude reference correction module that you will see. So in this one, the input message is an attitude reference, and the output message is the same type, attitude reference. And then you can specify a corrective attitude that gets applied such that this corrected body attitude actually would be equal to the reference orientation. And the math is in here. You can go through the kinematics yourself. So that's the purpose, prescribing orientations. The orbits get computed using F equals ma, typical orbital dynamics, but the attitudes dynamics are overwritten and prescribed by attitude reference messages. So let's look at the Python code quickly. Simulation, pretty standard, single process, single task, running 60 seconds here, and simulation time step is 60 seconds. It is huge. Before we kept using 0.1 seconds integration time because of the feedback control to make sure it's all numerically stable. And we're running for 3 times 60, so 3 hours simulation. Then you create your standard spacecraft, you create Earth, you add all together, you set up initial conditions. I'm only specifying initial position velocity because the attitude will be prescribed in this simulation. I have simple nav because I need to know from the hill frame module, where is my satellite? So I do need that, so that's the same. But then you can see in this scenario, if we're not using alternate body frames, we simply take the spacecraft attitude ref in message and subscribe it to the attitude guidance, which is the hill pointing attitude reference out. That's one option. Now you directly control it, but this will now say B becomes equal to R, not any other body frame, just your primary B frame. If you want to add a correction, we make this extra attitude correction module, set it up, and this is a C module. We add it to the task. This is the correction that we're doing. So we're doing a pi 180/4, what is that, 45 degrees rotation, actually about the 3 axes. That's our corrected, from body to the corrected one. And then we subscribe to the hill pointing output reference, that's our input. Then we apply this correction, and then that becomes our output. So that means the spacecraft attitude ref in message subscribes now to the output of this corrective attitude Basilisk module. That's about it. The rest of it runs, I mean, you can see there's the logger, you initialize, you run it, you pull the data, and then you plot it. So we can try plotting this here quickly. I do Python 3, scenario, attitude, prescribed. There we go. Oh, I can type it. And you can see how it actually would prescribe it. It just shows its inertial plot. If you looked at this in Visit, for example, you would see it tracking the hill frame or be in a fixed rotation relative to the hill frame, depending on if you're using the corrective attitude or you aren't.